We're now going to take a brief look at complex numbers. As some of you already knew, there is a number that is imaginary with the letter I. We started to hint at the existence of I when we looked at the quadratic formula and having a negative inside the square root. This is actually something we need for all even roots, or could need, in order to get solutions kind of forced. I apologize for my voice today. What makes this a complex number is that it has a real part and an imaginary part. It could be that one of those parts is 0. Of course, that's somewhat arbitrary. If the imaginary part is 0, then it's just a real number. But it could be that the imaginary, if you just have a purely imaginary number like 3i or just I, technically it's a complex number with only an imaginary part. So when you have something like this, often indicated by the letter Z, it's made up of A, which is the real part, written the real part of Z is A, and B is the imaginary part of Z. Written the imaginary part of Z is B, and we don't then include the letter I here. It's just the coefficient. And this form is called the Cartesian form of a complex number. We're going to look quite a bit down the line at polar and Euler forms of imaginary numbers. But for now, we're just going to look at this and use that to look at polynomials a bit more. So here are a few examples where we want to write the real and imaginary parts of each complex number. In this case, the real part of the imaginary number is -5. That's the part without the I. And the imaginary part of the complex number we see here is 2. Okay, this is already indicating that it has the I as the imaginary part. Here we have an example here. I can split that up to make it perhaps a bit more clear. So the real part of this complex number is the square root of 11/4. And the imaginary part of this complex number is pi over 4. The modulus is kind of like the absolute value of this. It's the magnitude or the length of, if you were to graph this, of a complex number. This is why it's kind of called the Cartesian form of a complex number. It's quite simple to graph on a complex plane that looks like the Cartesian plane, where your x-axis is the real axis, the y-axis is the imaginary axis, and say you had something like this number 2 plus 4i. Just go over 2 units on the real axis and up 4 units on the imaginary axis. So the modulus is the length of this. And really this is just the Pythagorean theorem. Okay, I'm going to do it here because the other word is in the way. You just have a right triangle. So 2 and 4 are the lengths of those horizontal and vertical sides of this triangle. And then we just use the Pythagorean theorem. Nothing too weird about this other than the fact that it's written so bizarrely or named differently. So if I wanted to calculate the modulus, or the magnitude of it graphed, we would just do the square root of 3 squared. Doesn't really matter that this is a negative, of course. The length is still the same. The square root of 45. This can be simplified. So that's 9 times 5. Remember, the square root of 9 is possible to take. So that would be the value of the modulus of a complex number. Powers of imaginary numbers. So remember that the definition of I, when we saw this and looked at it very briefly, or just kind of hinted at it, is that it is the square root of -1. That's kind of why it was invented, so to say, so that we could solve these things. If, for example, you had the square root of 9, you'd get 3. But if you have -9, or you could also get, I'm going to wait on the reason, you can also get -3 if it were 9. But putting the square root of a negative in here, we just can't do with real numbers because there is no real number that you could square and get a negative. So what we would do to indicate that is we take the square root and then say, but it's actually imaginary because of the negative. So you can say, well, that's the square root of -1 times 9. So square root of -1 is I times 3. Of course, it's kind of arbitrary with the negative here. 3i. Okay, so using that definition of this, a little bit more clear now, because that is the square root of negative 1. If you square that, of course, that undoes the square. That's inverse operations. And if you continue to do that and multiply it again by I, well, you get negative 1 times I. And so negative I. But if you do that again, you can see that with the power laws, negative 1, or the square root of negative 1, I squared times I squared, you get 1 times 1. And you get 1 again. And what you can do is you can keep using this kind of circle here. So as these are the powers, anything to the 0 is 1. I to the 1, anything to itself is 1. Anything I squared is negative 1. Oh no, that's really a terrible spot to have actually made a mark. Made a mark on top of that. It's a negative. I just made a mark to make it look like a positive. Let me make that super clear. That was literally the opposite of what I wanted. Okay, the reason they're kind of in this direction where you may see a unit circle looking different is like imaginary axis, real axis. Actually, take that back. It's the opposite. And repeat it as much as possible. So, for example, if I had, what is I to the 7th, I to the 1st, excuse me, to the 0, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, negative I. You can also quite simply add, subtract, multiply complex numbers, very similar to what you would with any other number, with any other variable. I is not a variable. Importantly, it's actually just a number, but it works similarly, except do remember that when you're multiplying imaginary parts, think of the powers and think of I times I actually being negative 1 and in general powers. So arithmetic on complex numbers. We're not going to look at division today. It's a little bit more complicated. That's for the next class. If you were to, I'm recording myself right now. Thanks. So if you were to just add and subtract these, be very careful with parentheses. So there's Z1, Z sub 1 is this first number, Z sub 2 minus Z sub 3. And if I were to make sure that I'm, in this case, it doesn't really matter, but distribute any negatives, any coefficients, 3 plus 4i. And then you can combine like terms. So 3 plus 3, those are my real parts. 4i minus 6i minus 2i is negative 2i minus 2 more I is negative 4i. Similarly here, so 8 in parentheses I minus 2 times divided by 4 minus 3. So nothing too tricky here. 8, and then I'm going to do this here. So that's actually 2 times this. 2 times I minus 2 is 2i minus 4. Distributing the negative 3, we get negative 9 minus 12i. And then we get, oh, that's it. I only had 2 here. So look at the corresponding parts, like terms. Negative 4, negative 13 here. 2i minus 12i is going to be negative 10i. And then a multiplication example where we're multiplying complex numbers. Z1 is 3 plus 4i times Z2, 3 minus 6i. Remember to FOIL. If you're thinking of it that way, multiply all the terms in the first by all the terms in the second. It's just kind of the distribution property expanded here. If you had more terms in each, you may want to use a nice organizer, maybe a table or whatever, but 3 times 3 is 9 first. 3 times negative 6 is negative 18i. 4i times 3 is positive 12i. And 4i times negative 6i is negative 24i squared. You do need to remember, though, that I squared is equal to negative 1, because the square root of negative 1 squared is negative 1. I'll just write these here still. We can still combine like terms. Okay. Negative 6i. And this is negative 24 times negative 1 is positive 24. So if you can combine these like terms now too, you get that 9 plus 24 is 33 minus 6i. And that's it for now.